6:27 on my clock. I guess that's 2 minutes. And yeah, I guess we should start. So yeah, as you might well know, so can everybody hear me first of all? And can you see the slides? All right, cool. All right, I see a lot of thumbs up. Okay, yes, that's good. Participation, I like it. So yeah, all right. Now that we have that cleared up, without further ado, I'm just gonna introduce myself and get right on it. So I'm Hong. I'm one of your TMs if you've ever seen me around. And today I'm gonna be talking about, or I'm gonna be giving a PyTorch tutorial, as you might already know. The point of this tutorial is also to be as interactive as possible. So I have uploaded a Jupyter notebook. So there are some slides, but there's also a Jupyter notebook that you can follow on the GitHub. I made an announcement on Canvas, and if you click on the link, you can access it. But yeah, so if you download the Jupyter notebook, you can follow the parts where there is any code, and it shouldn't be hard to follow. It should just run as long as you have PyTorch and Jupyter installed. And you don't need a GPU. I made it so that GPU usage is optional. But if you do have a GPU, you can uncomment some lines. And if you have CUDA installed, everything will run a lot faster. So yeah, let's start then. I don't know how familiar everybody is with PyTorch. So I tried to compile various tutorials into one so that you can have as much information available as possible. And also the Jupyter notebook can function as a standalone tutorial. If you just want to follow if there's something you forgot, you can just read the Jupyter notebook, to be honest. But I think it is good for you guys to join the lecture as well. So, all right. So let's get on it. So first of all, the structure that I chose for this lecture is one that I think would be a good introduction for y'all. First of all, I'm gonna go through what are the frameworks for deep learning and why use PyTorch. Then I'm gonna dig in straight into PyTorch, how to install it, briefly how to run it, and then yeah, we're gonna go do some technical stuff. What are the building blocks? And then we're gonna talk about optimizers, schedulers, data loaders, and then we will follow an MNIST step-by-step example, which is one of the most common data sets in vision tasks. Then we were going to talk about what an ideal project in PyTorch would look like, or at least how I set it up, which is kind of a conglomeration of what I've seen online and how other people have set up their big projects, because these projects can get really big, and it is good to manage them in a good way. And I'm going to provide some other resources like visualization tools, stuff like that, and other further documentation stuff. And finally, we're going to go briefly through TensorFlow and compare how TensorFlow differs from PyTorch for you to make an educated decision on whether you want to use TensorFlow or PyTorch. Because we're not here to tell you what to do. We're here to suggest, right? So first of all, we're gonna go over the framework, right? Once again. So where do these frameworks come from, right? So deep learning, although it's very commonplace now, it wasn't very commonplace 4 years ago or 5 years ago, and it was very painful to develop a full net if you didn't know what you were doing. So um, the reason these frameworks exist is because somebody came up with the idea that machine learning and deep learning specifically should be a tool for the masses, right? The common masses, as they would say. And this is why um, some developers started messing around with these huge libraries that provide easy ways to develop these massive networks. And for example, we have TensorFlow, PyTorch, MXNet, and Microsoft CNTK. Um, so in terms of history, as I said, I mean, the timeline is very short. We started with Yano and then Cafe, which was really widely used. But now mainly we use Keras, TensorFlow, and PyTorch. And I'm talking about both industry and academia. These are like the predominant players in some sense. So the point is the history is very short. There is not a lot to say about these things, and they are still evolving. For instance, TensorFlow 2 just came out, which I'm not gonna talk about. It's very new. It's shiny, and from what I've heard, is a little sloppy. So we're gonna go for the solid TensorFlow 1.15, 16. I don't remember, but yeah. So where do these libraries come from, right? They were pretty much all initially developed by academia, so universities, maybe in conjunction with a company. And then you also have CNTK, which is developed exclusively by Microsoft, and MXNet, which is exclusively by Amazon and a bunch of other people. PyTorch comes from NYU and Facebook. So if you're gonna work for Facebook, you're probably gonna be using PyTorch most likely. Um, and of course, TensorFlow is by Google. It's very commonplace. And I heard Cafe is very painful. I have not used it. And the other ones I'm not familiar with either. Um, so what are the important characteristics of these, right? So why would you want to use Cafe? Well, Cafe, the only advantage I've seen is that it is very portable, so you can grab it and use it on any machine, just because it's, I mean, it's a very low level C++ with C family framework, and uh, the problem is that it's low level, right? So it's gonna be painful to code in, and probably pretty hard to learn. Um, yeah, so TensorFlow, what are the advantages of TensorFlow, right? It's very rich in functionality. It has around like 2,000 unique commands, and but some people consider TensorFlow code very hard to read in terms of it's not very Python-like, which yeah, it's I think it's all right. I don't think it's that bad, but some people really do not like it. And then we have Keras, which actually works on top of TensorFlow usually, and it's very simple, and it's easy to use because you just have like layers available. It's like solving a puzzle pretty much. Um, but it is hard to implement anything sophisticated because you don't have explicit control of all the parameters and all the data, at least fine-grained control. And that brings us to PyTorch. PyTorch at least in my opinion, is flexible, easy to read, and honestly pretty easy to learn. And the only downside would be that it could get slow for very complicated programs, but I haven't found much trouble using PyTorch, and that's what I primarily used in my research. Okay, so once again, why use a framework, right? And why PyTorch specifically? Um, so mainly is because so why is PyTorch so easy, right? Because if you've ever used NumPy, for the most part, PyTorch looks pretty much the same as NumPy. You can still use like methods like dot shape and yeah, like slicing, and transposes, just like NumPy would do, right? So it's intentionally designed to be almost the same in functionality as NumPy, which makes it really easy to transition from NumPy to PyTorch, which we will see later on. And so, I mean, one of the reasons we use frameworks is because of automatic differentiation. If you've ever tried to do manual differentiation on some huge network, you have my respects, but I would not do it myself. Um, but yeah, this automatic differentiation allows us to build massive networks seamlessly, right? And last but not least, in fact, it's very not least, parallel computing. It's so PyTorch has a very good interface that allows you to use computational resources beyond Python's normal capabilities, right? So, and then we will see that if you do some operations on NumPy that can be parallelized, you can easily translate them into PyTorch and um, allow it to do it automatically on the GPU, and it's thousands of times faster in some instances, and it's honestly pretty amazing. All right, so now this is what I would really want everybody to see. This is exactly why we don't usually train stuff or networks on CPUs, because it's very slow. It's excruciatingly slow, it's painful, and you don't want to be sitting there for that long. So um, in some sense, it is not free to find computational resources, but luckily in our school and in various cloud platforms, there is a lot of free computational resources that you can access. I mean, if you don't have a gaming PC, uh, you can always use the university CHPC cluster machines, or you can just SSH to CADE. The CADE machines have all right GPUs that will run your stuff, albeit not at the fastest speed, but that's besides the point. They still perform way better than your CPU. So AWS and Google Cloud Platforms will provide you a first-time coupon where you can use some computational resources for free, but that's probably enough time for you to get familiarized with everything and decide whether you would like to continue using them or not. And Google Colab, I've had mixed experiences with Google Colab. Sometimes it works, sometimes it doesn't, but yeah, you can try that. It is free. That one's the very clear advantage of that one. It's always free. But how much computational resource you get, it's debatable. Um, yeah, so why, once again, to the question of why is PyTorch the one we picked, right? I mean, I tried using TensorFlow at the beginning, and it's a little harder to learn, but then again, I was new to deep learning. Um, but PyTorch, it was a breeze to learn, um, and it is gaining a lot of ground in, I don't know if industry, it has been gaining ground a little bit in industry from what I've heard, but in academia, it seems very predominant now. In fact, if you look at this graph, we can see that in some of the top conferences, you have like NeurIPS, ECCV, CVPR. The use of PyTorch has really increased with respect to other frameworks, and um, it's very useful to learn PyTorch, especially right now, because you will be seeing a lot of PyTorch code. If you're gonna read an academic paper, most likely they're gonna throw some PyTorch at you, and it is easy to read. It's easy to learn. So why not? That's the reason. So once again, we come back to the point of automatic differentiation, right? Why is this important? Because if you have any arithmetic operations, or most arithmetic operations, you can always compute subgradients, gradients and subgradients very easily. In fact, automatically. So you don't even have to look at any of the partial derivatives, and you will have a network running in no time. And this is very impressive, honestly. And so PyTorch would also allow, if the PyTorch framework does not automatically allow you uh, to or differentiate your operations, you can define your own gradients, right? So there's a lot of operations that are not differentiable, like sampling, but you might have come up with a workaround, and you can also implement that on PyTorch, which is nice. There's a lot of um, um, custom stuff that you can do to make PyTorch work for you, basically. And yeah, now that I've hopefully convinced you that deep learning frameworks are something worth your time, and that PyTorch is a good choice for a deep learning framework, we can go straight to installation and running of PyTorch. So here are just gonna talk about briefly. You just need a 64-bit processor and operating system. You need Python, obviously, and if you want to use GPU, which I would strongly recommend. In fact, some people say that you cannot do deep learning without GPU. Any non-trivial amount of deep learning. So yeah, you need an NVIDIA GPU. You can have an AMD GPU, but it does not work very well. So I have an old AMD GPU, and it does not work at all with TensorFlow or PyTorch. So I have to use my lab computer for anything. Yeah, so in terms of software, you will need to install CUDA on whatever computer you have. So what is CUDA? CUDA is the C++ controller kind of interface, software interface that NVIDIA develops to communicate with your GPU devices, so that you can tell them exactly what to do. And you won't be doing that, but PyTorch needs to communicate through CUDA, so you need that for this. So once you hopefully make sure that you do have the right computational resources, you can install PyTorch in one of two ways. So the first way, which PyTorch's website really recommends, is that you install Anaconda and run that command. I have not done that, so I cannot tell you how well that works. So the way I do it is I just use pip. So the second option is you just run this pip install command on Linux or Mac, and then this down here on Windows. So it shouldn't be that hard. It does take a little bit. It takes like 2 minutes, like, depending on your internet speed. I think the download is definitely the bottleneck. But anyways, so this brings us to the a hiatus on our slides here. So we're gonna switch actually to, where is it? There it is. So we're gonna switch to the Python notebook. Now you can really just follow directly if you have everything downloaded, and you can actually run all of this stuff. Um, yeah, and so I will be explaining all of this hopefully in detail. And yeah, so once again, there hasn't been any questions thus far, and I do want to encourage any questions if you have any, because I do want to make this interactive as much as possible. So if you have any questions, you can ask now. Checking the chat. All right. I guess there are no questions for now. I think it's very simple. Oh, so yeah, the question just came in and it asks, what is a TPU? So a TPU is so I guess all of you have heard about the GPUs. So GPUs are specifically designed for graphics processing. So TPUs are actually accelerators, hardware units that are specifically designed for tensor processing. So we will talk about that. This kind of deep learning frameworks. So deep learning is very conducive to using tensors because it is a very convenient, very nice way to represent your data. So these tensor processing units are extremely good for deep learning because they are specifically designed for such a task. And yeah, that's a good question. So yeah, in terms of computer hardware, people or computer architects have started designing more like task-specific computing units, and that's why we have like TPUs. We have, uh, I think they're working on like neural processing units specifically, and yeah, it's yeah. So that's a TPU. If that answers your question. Is there any other question? All right, so I will continue. You can ask questions anytime, right? Um, So here we come into our PyTorch tutorial, and the first thing you will see is once again in danger of being redundant, but you do need to install PyTorch, and you do not need CUDA though. So yeah, so how do you actually use PyTorch, right? Say you have already installed it and you made sure all your CUDA works, if you're using GPU. So it's simple, right? It's as if you were using any other library. So you just do Torch, import Torch Vision. So Torch Vision is kind of an add-on to PyTorch, which allows you to do a lot of kind of computer vision tasks, which we will use for MNIST. So one thing to notice is that you will need Torch Vision to run this file eventually. I think only for the MNIST bit though. So if you could install that, that would be great. And yeah. So we're gonna start with some Python basics here, or PyTorch basics. And so there are three very important units. So these are variables. These are the, like, what you would commonly call a variable in regular Python. These are three very important building blocks of what exactly of all the data structures that live within a PyTorch network per se. And these are tensors, variables, so layers, and modules. I guess I said three. I meant four. Yeah, so tensors. We're gonna first talk about tensors. Let me just give a brief overview of how these interact, right? So tensors are your basic elements. So this is where you're gonna store your data, and you've been familiar with like weight vectors, but so now we're gonna have weight tensors, and then vector gradients are going to be tensor gradients. And we can, so this is why it's so nice, right, to have this kind of structures, because tensors can store anything you would like in like a deep learning framework. So it's great. And then variables are just more abstract. It's an abstract data structure that represents a node in your computational graph. I'm gonna touch more on that. Don't worry about that. So it's basically a variable just contains the data and the gradient tensors. So, and this facilitates doing other stuff, like the stuff you want, right? Training specifically, because you will need the gradients and you will have to apply them to the data, or to the weights. And then of course you have layers. I think most people are familiar with this. Layers are just a bunch of neurons, or yeah, variables that are organized. So, like, yeah, I don't even know how to explain that, but yeah, layers are just conjunction of nodes that live within a network. And this is a side effect of how networks are usually organized, right? So they are organized through layers, and there is kind of like a pipeline to it. It's usually it's very linear, although you can build very nonlinear networks potentially. And modules are just substructures of networks, and we will talk about that later. I think hopefully as we keep talking about this, or like it'll make sense eventually. So once again, we're gonna talk about tensors. So tensors, once again, they are multi-dimensional arrays. I didn't think I said this, but yeah, that's what they are. So a 1D tensor is just a vector. A 2D a 2D tensor is a matrix. A 3D tensor is just, I mean, you have 3 dimensions of data, right? And so on. So now you can kind of see why this is important, right? Because in your linear classifiers, you were using a lot of 1D tensors and a lot of maybe a bunch of 2D tensors. But for deep learning applications where you have so many layers that interact with each other in so many ways, tensor representations are really good to store this kind of data, right? So why is PyTorch so nice for this, right? Because I assume that everybody has been using NumPy arrays. So why is it so nice? It's because PyTorch vectors are pretty, or tensors are pretty much the same thing as they once again, they have the same functionality, right, as NumPy arrays, and that is by design. So we're gonna talk about that. We're gonna see that in a little bit. But right now, let me just give you like a sample of a two-layer neural network that is doing a regression task uh, on some random data that is created, right? So here we have, uh, here I have like a basic design of just some random network. But if you, just so you recall what you learned in class, there is, so during training, there are various stages, right? First, you have your forward pass where you pass the data and you hopefully obtain an answer. Then from the answer, you compute a certain kind of loss that is going to represent how well or how badly your network performs. And then you have the optimizing step, right? Where it is usually gradient descent, but we'll see that is not necessarily the case, right? So the backward step, what it's going to do is going to compute the gradients and it's going to apply the gradients, right? So that's the descent portion of it. So well, we're gonna see this two-layer network in play here, and see if you can spot the forward pass, the backward pass, and the loss. I'm gonna delineate it anyway, so hopefully you can follow. So first of all, we have the import torch portion, which is, I think, pretty self-explanatory. And then we have here this is a line which talks about which device you're gonna use, right? So in my case and in everybody's case, this line is commented out because I'm not using a GPU, but you can always uncomment this to use your GPU if you would like. And this is, at least for now, this is how easy it is to switch from CPU to GPU on PyTorch, right? So now we're gonna see that these are the dimensions of our input vectors. We have 64 examples, and we'll continue from there. We create this random input and random output vectors. Once again, pay attention. They're random, so you're not working on any real data. This is a toy example, right? And of course, we're gonna initialize the weights of our two-layer network, right? So we have two sets of weights. We have W1 and W2. So yeah, and then we go to the training, right? So first we set our learning rate. It's just a number that you can tune potentially using cross-validation. Wow, that escaped my mind for a second. So we're gonna run it for 500 epochs here. And here we have our forward pass. The forward pass, what is it? We just pass our data through this network structure, right? So we apply a matrix multiply with W1 to the data, and then we do this ReLU thing, and then we matrix multiply again, and we do this ReLU, right? So that gives us the prediction or prediction for Y. Then this is the stage where we calculate the loss. So the loss here is just the mean square error, right? So we subtract the predicted label from the true label, or vice versa, and then we square it, and then we sum it, and yeah, we can print out the loss every 50 epochs. And then we do backpropagation, right? So we compute all the gradients, and so this is the backward pass. So we compute all the gradients as seen here, and you can see this is pretty much the same as NumPy, right? You can do element-wise operations. You can here multiply by 2, and this will multiply the entire vector here by 2, right? And this is exactly like NumPy, and this is why it's so nice. Uh, so you compute the gradients for all three of your important items, and then you just subtract the gradient on the trainable parameters. Uh, it's as simple as that. And if you try to run it, so if I click Control Enter, it will just kind of run instantly. It's a very small network, and then you can see the actual loss going down every 50 iterations. If you wanna run this, you want to experiment with this, you're welcome to. Okay, so here I'm just gonna point out that yes, so running on the GPU is just as easy as commenting out one line, right? So in this example, this example actually compares the exact operation on NumPy versus using Torch on GPU, right? So what we have is a matrix multiplication of a 3000 times 3000 matrix. This is why there's an A dot B here, and a torch matrix multiply A times B. And with NumPy, it takes 315 milliseconds, whereas on PyTorch GPU, it only takes 0.1 milliseconds, which it makes a huge difference when you're running thousands, millions of iterations or operations as such, right? So in some sense, you could technically run everything here on NumPy. In fact, you can compute your gradients manually and just store everything on a NumPy, or like store all the parameters and data and variables in a NumPy array, right? But that's you're gonna run into this problem really quickly. It's slow, uh, and also you don't want to compute gradients manually, but yeah. Those are both very important points, right? And now we're gonna move on to variables. I hope everybody understood the concept of tensors and how they're implemented in PyTorch. Are there any questions? Okay, so that's good. So what is a variable, right? A variable represents a node in a computational graph. And all you have to remember is that it stores both the data and the gradient. So here's what a variable class would look like. It contains the data, the gradient, and a creator, right? So the data is actually so x dot data. Suppose x is a variable. X dot data is gonna be a tensor, tensor as we explained it before, right? X dot grad, which is one of its parameters, right, or one of its members. It's a variable of gradients. So X dot grad is actually a variable. So it's another one of these structures. And so X dot grad dot data is actually your tensor of gradients, not X dot grad. X dot grad is a variable, but x.grad.data is going to be your tensor of variables. Yeah. So in the previous example, we actually computed the gradients manually, right? And we used tensors. But now that we have variables where it gives us like an easy way to store both data and gradients, we can use a little function here called autograd, which is a great function, by the way, because it allows you to compute gradients automatically. And this is one of the main reasons we are using deep learning frameworks, right? So as long as you're within the differentiable operations, PyTorch is going to do so it's going to calculate the gradients automatically for an arbitrarily large network, right? And this is honestly great. So what you're gonna do is you're gonna import the package, right? The autograd torch.autograd package, and you'll just see that as at a certain point, we do not need to compute the gradients as we did up there. We can just use loss.backward, and it's gonna do its magic. So if we look at the code here, so we're gonna keep looking at this two-layer network code, but we're just gonna make some improvements. We're gonna try to make it easier, so slimmer. We're gonna try to make it nicer, and we're gonna try to add more functionality towards the end, right? And so what has changed, right? So if you look at the x and y variables, so they are not tensors anymore. Now they are variables, and we have because x and y don't change, we're gonna set requires grad to false when declaring this variable, and then w1 and w2, they are trainable variables, so we're gonna say require grad true, right? So now that we have that, we can go to the training step, right? Where the magic actually happens. So in the forward pass, you will see that now it's only one line. Why is this? Because we do not have to store everything to eventually calculate the gradients, right? So we're just gonna do everything on one fell swoop. And yeah, so loss is gonna be the same. And then instead of calculating the gradients, if you see, we just did loss dot backwards, right? So this calculates the gradient automatically, and it was gonna store it in the grad parts of the variable. So we have, now we can access w1.grad and w2.grad and just multiply it by the learning rate and do its magic. So remember that w1 is a variable, and w1 grad is also a variable, right? And that's why you can do an operation like this, because it's just gonna multiply against the variables, right? So the observant mind is gonna see that we have this with torch.noGrad. So the reason we have this is that we do not want this operation to create anything, any update steps in the graph, because we don't need that, and we definitely don't want additional stuff on our computational graph that doesn't belong here. That's how you generate garbage, and you do not want that. And also, you have to manually set the gradients to 0, right? So that's something to remember, because the gradients are gonna differ at every iteration, and not setting them to 0 is a mistake. So if we're gonna, so we can run this just the exact same as the one before, right? And we're gonna get similar results. Maybe they'll vary a little bit. Yeah, this will let us continue to the next step, right? This is another level of abstraction, which is layers. So we saw that we declare the variables, and those form layers, right? But so layers are these abstractions of frequently used computational nodes, right? It says graphs, but it means nodes. So yes, so what are some very frequently used computational nodes, right? So Torch NN will provide these layers. In particular, if you do any amount of like NLP or computer vision, you'll see a lot of convolutional layers, either one-dimensional, two-dimensional, three-dimensional. You'll see transpose convolutions. Yeah, wow, that took a long time. All right, so you're also gonna see max pooling, you're gonna see dropout, you're gonna see linear layers. Linear layers are pretty basic. And also it will allow you to do losses. So you can have the MSE loss, you can have the L1 loss, binary cross entropy loss. You can have you can have any loss you want. There's a list, but you'll have to go to the documentation to reference something like that, right? But it gives you a lot of options, and you have very nice building blocks for your network, right? At this point, so now that we have this layers tools, we do not have to use variables, right? Although we discovered that variables are very nice, uh, we can, for the most part, just forget about variables and just use layers. We can think about variables when we actually need them, right? But usually you want to make your code simple, you want to make your code short, so layers are a great way to do that. And we're gonna see it right here, right? So we write the exact same code that we had before, but we use layers instead of variables, right? So now this brings us to the concept of a model, right? Your model is gonna be your entire network usually, uh, and your model is gonna obviously have an input and an output, right? You're gonna feed stuff to your model, and it's gonna output stuff. That's the whole reason we do this, right? We have a query, we have a question, and we want an answer for it, and this is what this will allow us to do. So here we're declaring the model, right? We're telling it that you're gonna sequentially have 4 layers, or there's 3 layers in sequence, right? You're gonna have a linear layer, you're gonna have a ReLU, and you're gonna have another linear layer. And this is exactly what it's telling it to do. And this is exactly what we did before, right? So our network is still the same, but now we're gonna use this NN layers, right? So if you see the loss function, instead of being defined so the loss function, instead of being defined explicitly, right? We're gonna use this PyTorch function, which calculates the MSE loss, and there's a sum reduction, so that's gonna be an MSE. So why is this very important, right? Because if you're running on the GPU, PyTorch is gonna do even these calculations within the GPU, which allows you to not have to copy back any data, and it's basically a very explicit way to say to tell PyTorch to do the stuff that you don't want to think about, right? So now if you look down here, instead of having the entire computational graph laid out for PyTorch, we've already declared a model. So we can just say the prediction is equal to the model with this certain input, right? And it's just gonna give us the prediction. It's just gonna apply these sequential layers to the input data, and it is gonna give us a prediction. And once again, you compute the loss, as I mentioned before. Now you're gonna do 0 grad here, because you wanna clear the gradient, just like we did before, right? And then you're gonna do loss backwards, just as we did before. And then torch no grad, just like we did before. But now, instead of saying, oh, just subtract this from this, because we don't have an explicit representation of these variables anymore, right? We can't just say W1 is equal to learning rate times W1.grad, right? Because W1 does not explicitly exist. So what we're gonna do in this case is we're gonna say for every parameter in the model parameters. So the model is gonna have a series of parameters, and you can iterate through them, right? So you're just gonna do this. You're gonna do the descent step, right? So it's similar, but you have to you have to reference all the parameters, right? Because they don't have an explicit name anymore, because you didn't name these variables. But yeah, so this is a lot nicer, right? We have a lot of comments, but really few lines of code now. It's nice, it's compact, and we can run it just the same way. Control Enter, and it's gonna take 3 seconds, and here we have the answer, right? Mm. Okay, so is there any questions about layers, or are there any questions about layers, or variables, or tensors, or anything, as a matter of fact? I'll take that as a no, and we will continue straight to network modules, right? So network modules, as you might already have guessed, they are just a bunch of layers or variables. You can combine them, make some intricate network module. But these are just abstractions of network substructures, right? So, for instance, sometimes your network can be comprised of various like subnetworks, right? So maybe you want to repeat one structure various times in your network. Well, you can just make some blocks, and just like Legos, you can just put them together, right? And for instance, one of the very commonly used blocks, it's probably gonna be the ResNet block, right? Very widely used in the literature because of its power to converge quickly, in like especially in imaging applications, right? And so this is exactly why this will allow you to build um, massive networks in like a neat way, right? But of course, before you do that, you have to learn how to build this, right? So the way to build this is you're gonna have a network class actually. So you're gonna build a network class which has two methods, two mandatory methods, right? So you have init, uh, which is where you're gonna initialize all your layers. As you can see, it references the torch NN library, and it adds all the layers. And then the forward network, or the forward method, is where you're gonna define your computational graph. Um, so you can explore this code more in detail, but basically you're defining your computational graph in another way, right? Last time we just used sequential, but something like this will allow us to build more complicated, less linear structures, right? So if we look at the code, our two-layer net now is just an init, which has the two linear layers, and then it will actually return the prediction, right? And then apply the ReLU on the forward pass, where the computational graph is defined. All right, so what else has changed, right? Nothing much. We just defined the network in another way. And so instead of the model being a sequential bunch of layers, now we have a fully fledged network, right, that we have predefined. And we have the inputs, we have the dimensions here, and it's gonna create our model for us, right? This is this PyTorch functionality. So if I just press Control Enter, it's gonna do the exact same thing, right? So great. So that concludes the part where I talk about the basic data structures, or like the data structures, the building blocks that comprise this deep learning framework, right? Are there any questions? I'm gonna go a little bit faster because there's still a lot of material to cover. But all right, now we're gonna move to the optimizer. So thus far, we have explicitly told the network to do a backward step, right? We have gone through all the parameters and told it, okay, do this, do this, do this other thing, right? But this is not necessarily the case, especially when you have more complicated training methods. Like, so we've been doing gradient descent thus far, right? So, but there are other training schemes like AdaGrad, like RMS Pro, like Adam. So PyTorch offers this optimizer class, right? That will give you the option to automatically choose an optimizer. So now that you have your gradients, it's just a matter of applying the gradients, right? So the optimizer defines the way in which you are going to apply the gradients. So what what you're gonna do is you're gonna initialize this optimizer at the beginning, and then you're gonna specify a learning rate, and then you're gonna give it the model parameters. So you can actually pick and choose which parameters get optimized. So that is nice. And you do an optimizer step every time you are within your training epoch, right? So that is gonna apply uh, this optimizer step. So so what has changed, right? Just like before, we have our network, we have so we declare the model, but now we're gonna add this optimizer at this step, right? So this optimizer is gonna be a stochastic gradient descent optimizer. So nothing much has changed. But now instead of iterating over the parameters, we're just gonna do so first we're gonna clear our optimizer, then we're gonna do the optimizer step, right? If you see there's no iterating over parameters, this is gonna do the stuff automatically for you. You don't have to think about it, and it's simple, right? And you can see our how much our training step has shrunk, right? And now it's like what, like 5 lines that matter. So this is great, right? If I press Control Enter, same thing, we get pretty good results. So yeah. So that's the optimizer. Are there any questions about the optimizer? Okay, so we're gonna move on to the scheduler now, right? So we talked about the optimizer, and yes, the optimizer is so nice, right? But then it seems to be stealing the ability to really micromanage your training, right? Well, that's not necessarily the case because the scheduler is here. The scheduler will allow you to like tune the hyperparameters the parameters of the optimizer as you learn. So at every epoch is gonna allow you to, for example, decrease the learning rate. That's what step LR would do. So every step size epoch is gonna multiply the learning rate by gamma, right? So how do you use the scheduler? So very similar to the optimizer. So you will declare your optimizer and actually pass it to the scheduler, right? And within your epoch, you're gonna do a scheduler step in addition to your optimizer step, right? So what we'll see here is what I explained, right? So the scheduler will live here. You're gonna pass it the optimizer. So the step size is gonna be 1. So it's gonna multiply by a factor of 0.99999 every epoch, right? That's what the 1 means. So this is what we see here, right? So after the optimizer step, we do a scheduler step. And this is just gonna multiply it by a certain amount. So in this application, I picked gamma 0.9999 because there is not much need for decreasing the learning rate. But in some applications, you will see that it is very important. Yeah, but we can run this like before, and we're gonna have the same thing. And finally, this is gonna be kind of branching out a little bit, and we're gonna talk about data loading, right? So PyTorch offers an automatic framework for data loading. And you're gonna say, well, data loading, that's easy. You just have vectors of data, right? Well, not necessarily, because sometimes you wanna do automatic batching, you wanna do some like really weird processing stuff, and yeah, so PyTorch data loaders also do a lot of GPU operations in a more efficient way than what you could do, right? Um, so basically, the data loader, we're gonna go over this toy loader, has three methods, right? The init method, the get item method, and the length method. So the init method, you're just grabbing the data and storing it into some variables, right? Here we're gonna store our random x and our random y, and we're gonna set the length to the shape of x, right? So now we're gonna get, so the get item method is gonna return the item, right? You're just gonna return a pair. So it's gonna return x at index and y at index. So this is just a training example, right? And the length is just gonna return the length. And this is simple, right? So what you're gonna do within your code is that you're just gonna do data set is equal to toy loader. So you're gonna create your data set and you're gonna load it. And you're gonna feed it to the train loader and you're gonna give it some parameters, right? Our data set is gonna be this data set that we just loaded. And then the batch size and the shuffle true. So there's a lot more options. There's a ton of stuff that you can do with this data using the data loader. And you can look at this later on, right? But now if we look at our code, the data loader is gonna allow us to create the data, and then we're gonna load it, right? So, and after loading it, if you see, now we can do batch training, right? Which is easy. So we're just gonna add another loop within our epochs, and we're gonna grab the data. So it's gonna get enumerated out of the data loader first, right? And then we're gonna create our x and y vectors, vectors in this instance. So yeah, and we're gonna make them variables, right? So we can work with them with the gradients. And then we're gonna do same thing as before. We're gonna do a prediction, we're gonna do a loss, and then the same optimizer backward and step scheme, right? And if you think about it, the scheduler still steps every epoch, so this is outside that for loop, and that basically is how you use a data loader. If you think about it, we did batch training without any issues. We just used the data loader and it did it for us automatically. So if we press Control Enter, you'll see that now every epoch it trains on 2 batches, right? And it's gonna try to, I mean, it's doing the same thing, right? Except in a batch way. Yeah. So finally, this brings us to the MNIST example, right? I don't know if there's any questions up till now, but yeah, we're just gonna go straight into the MNIST example. So the MNIST example is really simple. In some sense, we have learned all the tools already to understand this MNIST example, but this will give you like a sense of how a real project So this is a small project, right? But like how more or less like a big project, the building blocks would be like, right? So what are the functions? What are the classes that you have to declare? And this will be nice, right? So if you don't know about MNIST, it's just an image handwritten digit image data set that will contain the labeled digits, right? So every digit, every image that comes with MNIST is gonna say, like if it's a 9, it's gonna say, oh, it's a 9, right? So I mean, I think everybody's familiar with it. So and the network we're gonna have is this one, right? It's a very simple network. It's you have a bunch of convolutional and max pooling layers. You're gonna apply ReLU, and unlike what the picture says, we're actually gonna apply dropout after if each max pooling layer. And this is like a standard MNIST classifier using deep learning. So like there's not much to it. Let's dig straight into the code then. So you first you import a bunch of stuff. It's just so you can like have access to Torch NN very easily. You have some functional things. You have your optimizer, and then you have your scheduler. This is and data sets, right? This is all stuff that we have talked about. And then first, this should look familiar to you. This is just how you declare a network, right? So here, the convolutional networks, the fully connected layers, and the dropouts are declared. And here you define your computational graph, right? What we saw up above. So, and also you have a training function. So the training function is just like we had before, right? The same thing. It's doing batch training. It's enumerating the data. Here it's moving the data to device here, but device is just CPU in this case, unless you do have a GPU, and it's doing optimization. It's printing it's doing some backward step, some optimizer step, and it's printing the errors, right, in a nice format. So, and then test is pretty much the same. But you don't do any training here, right? So you add this line that is model eval. So that will just put your network into evaluation mode, which means that batch norms and dropout layers will work in evaluation mode. And this is important because you don't want them to perform in training mode. And here in train, you'll see that it says model.train, right? So these are just things to consider when you're building your own network, especially when you have batch norm and dropout layers, right? So this is gonna be something similar. You're just gonna iterate over the test loader, which is the way to, or the data loader for the test data, and then you're just gonna compute the same losses, right? You're gonna test for correctness, and you're gonna just aggregate everything and print out the losses, right? It's pretty self-explanatory. And then this is just something I use to get rid of the argument stuff. I really wanted to make it look as real code as possible, but some things don't work on Python on Jupyter notebooks. So we're gonna go to main now. So main will have primarily, so you're gonna have your arguments first, right? Like this will allow you to change the batch size, the epochs, and this is just a nice interface for a user potentially, right? And then you're gonna have your CUDA stuff. The CUDA stuff, you can just look at it. It's pretty self-explanatory. So if you have a CUDA device, you'll use the CUDA device. If not, it's going to use the CPU, right? And that's what your device is going to be. And here is the data loader, right? We've seen this before. And we will see here that a lot of transformations happen on MNIST, right? First, we're gonna do compose, we're gonna do to tensor, and we're gonna actually do normalize. Um, and this is some pre-processing that gets done automatically in some lines, right? And this is why such data sets are also so nice, right? Because you can just directly do this. And this will just grab the MNIST data for training and grab the MNIST data for testing. And that's it. It's just these few lines, right? And this should look very familiar to the code before. And then you're gonna have the model, which is just your net, which you're gonna send to the device. And then the optimizer, in this case, we're gonna use an ADA delta because it performs very well on this MNIST data set. Then you're gonna use the scheduler, and then you're gonna train using your options, your functions, right? And at the end, we're gonna save the model. And saving the model just saves the model to a file. And it's as simple as that. And you will be able to load the model later on. And um, hopefully this was like a good overview of the building blocks, right? We saw that everything is neatly organized. There's a training function, there's a testing option function, there's a class that contains your network, and you can put all this in different files, right? Which makes even huge projects very nice. And here just an overview of how to save and load. You can look at this later on. It's not that important. And I added some bonus things if you want. I've can never use this before, just pre-trained models and some custom weight initialization. But if you want to look at that, you can, but I'm gonna just skip it for now because we have a little bit more to talk about. And just some closing remarks. Hopefully this was helpful for you to have like a step-by-step introduction to this PyTorch framework. And I would strongly recommend you to go back and just run this code and see really where the differences in these codes are, right? It's just a simple network, and then you finish with MNIST, and you'll be able to quickly understand what's happening. And hopefully this was helpful, but we're just gonna close with some additional resources that you can use to make your PyTorch experience smoother. And yeah, just let me know if you have any questions now. This is a good time, so I'm gonna switch to the slides. So I'm assuming there are no questions. So I'm just gonna dig straight into it, right? So the next part, now that we've looked at all the nice things that PyTorch has, so how do you build your own project, right? Honestly, there are three stages that everybody says that are important for building your own project. So there's data preparation, there's model design, and there's the training strategy, right? And you have to be very careful with all three of them because they are because none of them can be overlooked. So data preparation, as you might have seen already, is very important in any machine learning application. So you have to familiarize yourself with your data, and you have to know how to work with it, right? So data loading is also very important. You have to be able to manipulate your data easily. And then you will have model design. Obviously, designing your network is very important. That's where a lot of research lies still, right? And then, of course, your training strategy, because sometimes you want to train one part of the network independent from other parts of the network. So you really have to be very careful, right? And of course, tuning your hyperparameters like the learning rate, very, very essential. Yeah. So, um, I'm just gonna go over real quick how I structure a project on Git. Basically, I have all my networks, trainers, and data sets in this, and data set pre-processing stuff in a lib directory. Um, and then I will have an input and output directory, and then the source directory is gonna comprise all of my most essential code, right? That will use everything to run stuff. So I think this is a quite sustainable way to build big networks, and hopefully that will be useful to you. But yeah, that's how you're supposed to do a project, kind of. But yeah, honestly, most of the times when I start a new project, I just copy some code of the closest network that I want to implement. I just copy paste it into like a new Python file and then just work with that. So that might also work. Anyhow, so let's talk about some other resources just briefly. So I use this PyTorch summary thing a lot because it lets me visualize like how much memory am I using, what my network looks like, and this is before even training, right? And this is really nice for me because I can debug even before starting, right? And of course, you have stuff that can visualize some layers, some data, like PyTorch VSTEM, and then TensorBoard will let you like visualize the training itself, right? It will let you visualize the loss, and like just a lot of yeah, it gives you a lot of tools to be able to tune hyperparameters as well, right? Okay, so there's other resources, the standard documentations. There's some basic code that you can copy paste, as I said, and you can just follow the links if you're interested. And last but not least, I just want to briefly go over some TensorFlow stuff. I know it's time, so I'm just gonna say the basics, and if you want to stay for like an extra minute, you can. So TensorFlow is very similar to Keras or to yeah, PyTorch, right? Uh, but it does have three different levels. So the primitive, layers, and the Keras level. So they will allow you to have different levels of abstraction, right? Just like PyTorch's tensors, variables, layers, and modules, right? So we'll go over briefly just this MNIST code, and you can access this code by just clicking this link, um, and you will notice a huge amount of similarities to PyTorch, but it just carries itself in a different way. And maybe you will be able to see why people like PyTorch more than TensorFlow or vice versa. Um, and yeah, usually people think TensorFlow code is some more primitive code, primitive level code, but you'll be the judge of that, right? So we can see that we'll divide it into different chunks. Here's the data loading for TensorFlow. So one thing to notice is that this TensorFlow implementation of the MNIST network, it's so the network it implements and the functionality is a lot less than what we implemented in PyTorch. But this is just a basic example, right? So if you see in TensorFlow, you directly import MNIST from this TensorFlow examples tutorials.mnist, which is nice, but I have never written my own data loader in TensorFlow, so I don't know how hard it is. So you'll have to be the judge of that, right? And PyTorch, it does have a few more lines of code. In fact, a lot more lines of code. But there's a lot of stuff going on here, right? There's a lot of options that this provides to you, and that's very nice. Um, so now the model, right? A TensorFlow model is also it's very similar, right? It's very similar to the PyTorch variables. Actually, you have your inputs, which is x and y. You have your weights, which are variables. Your biases, also variables. You create a function instead of a class for your network, and then you apply the same thing, right? Uh, your model is just going to be your neural net, which is a function that takes x and returns your logits, which are the the predictions, right? Then you do a softmax and you obtain your predictions. Um, and it's pretty much the same as PyTorch, except the structure is slightly different, right? Then you have the optimizer. Here's where TensorFlow is a lot more specific in what it wants you to do. So you're gonna have a lot of stuff that you have to do manually. You have to do reduce mean and then cast instead of just an MSE loss, right? You're gonna compute accuracy, yeah, there's not a lot of stuff. You do have to initialize all the variables explicitly in TensorFlow, right? If you see the loss, the optimizer, um, and the training operations, pretty much the same, just different syntax. And then we go through the training. So PyTorch training, we built our own function and then we just iterate through it with the scheduler. And then TensorFlow, you have to, so here you have you have automatic batch, right? Just because it's actually a very well established library. So you have access to this mnistrain next batch function. And then you do this session run operation, which is what initializes the training session, the network session per se. You compute once again the loss and accuracies, and yeah, so this session run is gonna do your training operation, right? And you're gonna fit it the dictionary of your input data, and here you have it. This is how you train on TensorFlow, and think about it. It's very similar, right? So far we had the same structure, and all right, so yeah, finally we're gonna talk about the testing, right? Which in TensorFlow is just simple. You just feed it the dictionary, and then yeah, it compares almost the same with PyTorch. The basic principles are the same, but here PyTorch, our PyTorch implementation, it prints the test data every epoch, right? So that is a nicer way to visualize stuff. But yeah, I hope this was like a good, sorry for keeping everybody late, but I hope this was like a good comparison between PyTorch and TensorFlow. Sorry it was so rushed, but yeah, I hope you did learn a lot. And finally, I wanted to end with some general questions, if you have any. Again, sorry to keep all of y'all late. And somebody was way ahead of me, and they were saying that the PowerPoints I posted have no TensorFlow slides. Okay, I'm gonna fix that. Don't worry. if I don't, just send me a message. Yeah. But any other questions? I hope this was helpful. I had to go a little fast at some point, but I mean, I think the TensorFlow or the Jupyter notebook can be like a standalone tutorial if you want to reinforce it, if you want to reinforce your knowledge. But yeah, I guess there are no questions. So thanks for attending. And I'll see you next time.
Thanks for home.
All right.
Yeah.
Thank you. That was fun, everybody.
Yeah, great. Yeah. So I have recorded the video and I will upload very soon. Okay. See
All
you.
right. Perfect. See you.
See you.
Bye.